This is Euclid Book 10, proposition number 113. This is one of the longest proofs of Euclid Book 10, but fortunately it's also one of the last. We are down to our final three, and the other two proofs after this are a lot shorter. Thank heavens. Okay, it says, the square on a rational straight line, if applied to an apotome, produces as breadth the binomial straight line, the terms of which are commensurable with the terms of the apotome and in the same ratio. And further, the binomial so arising has the same order as the apotome. Okay, let A be a rational straight line. That's this one right here. And BD an apotome. This is an apotome right here. Okay? And let the rectangle BDKH. Now, at this point you're saying, well, how did we get BDKH? Well, this rectangle has two sides the length of BD, and the other two sides the length of KH. Okay? Probably I should have relabeled all this, but that's okay. Okay. Now, the area inside of here is going to be exactly the same as the area inside of here. Now, what is this? If we take the line A right here, and we turn it into a square, and all four sides of this square are going to be the length of A, that's what that is. So, the area in this rectangle is going to be exactly the same as the square on this. Okay? So that the square on the rational straight line A, when applied to the apotome BD, produces KH as the breadth. So what we're doing here is we're applying the area of this square onto the line BD, which will give us the breadth of KH. That's what's going on here. I say that KH is a binomial. The first thing I'm going to say is that length KH, which is this length right here, is a binomial. Okay, it's a binomial straight line, the terms of which are commensurable with the terms of BD, and in the same ratio, and further, KH has the same order as BD. For let DC, okay, what is DC? That's the length from here to here. It's going to be annexed to BD. Okay, therefore, BC and CD, okay, BC and CD are rational straight lines commensurable in square only. This is by Euclid Book 10, proposition number 73. Let the rectangle BCG be also equal to the square on A. So now we're going to construct another rectangle. That's this one right here. Two sides of this rectangle are the length of BC. The other two sides of this rectangle are going to be the length of G. And this area is going to be equal to this area. Okay. Now we know that the square on A is a rational area. Therefore, the area inside of here is also rational, and so is the area in here. Okay. Now, we're going to apply this area to this line. Okay. Now, that means that G here, this G right here, is a rational straight line, and it is actually commensurable with BC. And that's by Euclid Book 10, proposition number 20. Since now the rectangle BCG, which is this one right here, is equal to the rectangle BDKH, which is this one right here, now we're going to start ratios. Okay, you see a whole list of these ratios right across here. So I want you to write these down and remember them. Okay, as CB is to BD, okay, this is to this, so is KH to G. Now keep in mind, all four of these are lines. All four of them. Okay, and that's by Euclid Book 6, proposition number 16. But BC, this length right here, is greater than BD, which is this length right here. Therefore, KH, which is this length right here, is greater than G. Okay? let KE, which is this length right here, we're going to make this equal to G. I know it doesn't look equal to G in this diagram, but we're going to make it equal to G. Okay. Therefore, KE, which is this right here, is commensurable with BC. Okay. And since as BC is to BD, there we go, so is KH to KE. Now what did we do here? We said that KE is equal to G. So what we did was we took this ratio right here, we rewrote it, and we replaced the G with the KE. And that's how we did that. Therefore, convertendo, as BC is to CD, okay, as BC is to CD, so is KH to HE. Okay? Now let's do that one more time. As BC is to CD, so is KH is to HE. That's how we got this. That's by Euclid book. This is by Euclid Book 5, Proposition number 19, Porism. Let it be contrived that as KH is to HE, now what is KH? That's this line right here. What is HE? That's this line right here. So is HF to FE. Okay, so is HF to FE. Therefore, also the remainder KF, this is the remainder KF, is to FH. So as KF is to FH, as KH is to HE, as KH is to HE. Okay? That is, as BC is to CD. And that's by Euclid Book 5, Proposition number 19. But BC and CD, okay, this is BC and this is CD, they are only commensurable in square. Therefore, KF, which is this one right here, and FH, the only time those two lines are commensurable is when they're squared. This is by Euclid Book 10, Proposition number 11. And since, as KH is to HE, so is KF to FH, okay? While as KH is to HE, so is HF to FE, this little thing right there. Therefore, also, as KF to FH, as KF is to FH, so is HF to FE. So is HF to FE. That's by Euclid Book 5, Proposition number 11. So that also, as the first is to the third, so the square on the first is to the square on the second, which is by Euclid Book 5, Definition number 9. Therefore, as KF, which is this one right here, is to FE, which is this one right here, so is the square on KF, which we've made right here, is to the square on FH, which is right here. But the square on KF is commensurable with the square on FH. This is commensurable to that. Therefore, KF and FH are commensurable in square. These two are commensurable in square. Therefore, KF is also commensurable in length with FE. KF is commensurable with FE. That's by Euclid Book 10, Proposition number 11. So that KF is also commensurable in length with KE. Okay. KF is commensurable with KE. That's by Euclid Book 10, Proposition number 15. But KE is rational. This line here is rational. And is commensurable with BC, which is this line right here. Therefore, KF, which is this line right here, it's also rational, and it's also commensurable with BC. This is by Euclid Book 10, Proposition number 12. And since, as BC is to CD, as BC is to CD, so is KF is to FH. Okay? As this is to this, so is this is to this. Okay? Alternately, as BC is to KF, as BC is to KF, so is DC to FH. That's by Euclid Book 5, proposition number 16. Alright. But BC is commensurable with KF. BC is commensurable with KF. Therefore, FH, this line right here, is commensurable with CD. That line right there. That's by Euclid Book 10, proposition number 11. But BC and CD, okay, this is BC right here and this is CD right there, they are rational straight lines and they're only commensurable in square. Therefore, KF and FH are also rational straight lines by Euclid Book 10, definition number 3, and the only time they're commensurable is when they're squared. Therefore, KH, this right here, is a binomial. That's by Euclid Book 10, proposition number 36. If now the square on BC, that's this, is greater than the square on CD, which is this, by the square on a straight line commensurable with BC, the square on KF, which is this, will also be greater than the square on FH, which is this, by the square on a straight line commensurable with KF. This is by Euclid Book 10, proposition number 14. And if BC, line BC, is commensurable in length with the rational straight line set out, so also is KF, which is from here to here. If CD, which is this, is commensurable in length with the rational straight line set out, so is FH. But if neither of the straight lines BC, CD are commensurable with the rational straight line set out, then neither of the straight lines KF, FH. Okay, so if BC is not commensurable with the rational straight line set out, CD won't be commensurable with the rational line straight out. If KF here, if KF is not commensurable with the rational straight line straight, you get the idea. But if the square on BC is greater than the square on CD, by the square on a straight line incommensurable with BC, the square on KF is also greater than the square on FH, by the square on a straight line incommensurable with KF, which is by Euclid Book 10, proposition number 14. And if BC, which is this line right here, is commensurable with the rational straight line set out, so also is KF, which is this line right here. If CD is also commensurable, so is FH. But if neither of the straight lines BC, CD, so if this is not commensurable and this is not commensurable, neither is KF or FH commensurable. Therefore, KH is a binomial straight line, the terms of which KF, FH are commensurable with the terms of BC, CD of the apotome and in the same ratio, and further KH has the same order with BD. That's what we were trying to prove. Well, at least now you know how the proof actually works. I can't say I know everything about the proof, but you know how it works. Anyway, we have 2 more proofs before we're done with Euclid Book 10. Then we can go on to 3-dimensional proofs, which I talked about at the beginning of Euclid Book 10. Alright, I will tell you more in a future video. Stay tuned.